This video is to help explain the activity 4.5, the Lewis dot diagrams for ionic bonds. Okay, so remember for ionic bonds, they're different than covalent because remember covalent was sharing electrons. Ionic is giving or taking away of electrons, causing the atoms to become ions, which are charged particles, and then those opposites charges are what attracts them together and holds them together in the bond. Okay, so ionic bonds are usually going to be formed between metals and nonmetals, and the key distinction here is that the electronegativity must be greater or equal to or greater than 1.6. Okay, because if it's below that, it can technically be a covalent bond. They can share electrons. Okay, so here is just a little quick diagram that shows. Okay, we have sodium that has 1 electron, chlorine has 7, so it really wants that 1. Sodium doesn't really care. It would take a lot to get 8 electrons, so it would rather give away its electron than try to find 7 other electrons. Okay, so it gives that electron away. Okay, the chlorine now has that electron because it got an extra negative charge particle of the electron. It now has an overall negative charge. Because the sodium got rid of its negative charged electron, it is now more positive. Because we have a positive and a negative ion, they are attracted to each other, and that causes the ionic bond. So whenever using Lewis dot to help us create ionic bonds and see how they would bond together, here are the different steps. I'm just going to go through the steps as I go through the example that I have for you. I actually have 2 different examples. On page 3 of the activity, I do have the electronegativity chart for you to reference in order to calculate what the electronegativity difference is to make sure that it's actually going to be an ionic bond. You'll notice up at the top I have the column numbers, okay, the 1A, 2A, 3A, 4A, 5A, 6A, 7A. Remember that those numbers tell us the number of valence electrons, which is helpful when drawing the Lewis dot diagram. Okay, so if I were to pick like calcium, okay, it's in column 2A, so it would have 2 valence electrons. If I was going to pick, let's say phosphorus, okay, it's in column 5A, so it would have 5 valence electrons. So just kind of as a refresher on that. You'll also notice that in blue I have the oxidation numbers. That'll come in handy a little bit later. I'll kind of show you guys a shortcut to doing the ionic bonding. And then just also note that here the noble gas, column 8A, has been removed just because most of, or a good chunk of the noble gases actually don't even have electronegativity, and they're not going to be bonding with other elements generally. Okay, so that's just been removed because they don't have electronegativity. Okay, so for example 1, if we have lithium and chlorine, first we need to determine if they will form an ionic bond. So if we go back and look at lithium, it has a valence electron or electronegativity of 1. Okay, and then chlorine has an electronegativity of 3. Okay, so if we subtract 3 minus 1, we get that the difference is 2, which is greater than 1.6. Thus, we know it's an ionic bond. Okay, so we're going to draw the Lewis dot structure. I just put a note here, what I just went over with you guys about determining the valence electrons. So because lithium is in column 1, and then chlorine is in column 7A, okay, lithium will have 1 valence electron, chlorine will have 7, okay, which is what I've drawn. Okay, remember that you need to pair them up properly when going around. Chlorine's pretty easy because there's only 1 that's unpaired, but in my next example, I'll show you why it is important that you kind of draw them out properly. Okay, the next step is to move the unpaired electrons to fill the outer shell of the nonmetal. So I'm going to take lithium's, he doesn't really want to hold on to it, so he's going to let it go and give it to chlorine because chlorine really wants an electron to fill and have 8 electrons. So it's going to transfer over. Okay, so when it transfers, lithium is going to become more positive because it lost a negative charge, so it's going to become a positive 1. Okay, generally for ions, we don't put the 1. You could, it would still be correct. Okay, and then because chlorine gained 1 electron, it's going to become negative, more negatively charged by 1. So we could have put -1 there as well. But generally they just put plus or minus if it's just 1. Okay, and so the key thing to notice here is that the ions recorded match the oxidation number for each element. So if we go back and look at lithium and chlorine, lithium, which is in column 1A, is supposed to have an oxidation number of +1, which is what we found. Okay, and chlorine, if we look at it in column 7A, is supposed to have an oxidation number of -1. So it does match. And here in a little bit, I'll kind of explain to you the shortcut that you can use the oxidation numbers to find the formula. Okay, so because chlorine only needed 1 electron, lithium had 1 electron to give, they are now happy, right? Lithium got rid of its valence electrons, so now it kind of got rid of its outermost shell, so now it's full in the next shell, even though we're not showing those valence electrons anymore. And then here, chlorine now has 8, it is happy. Okay, so our formula, we have 1 lithium and 1 chlorine, so LiCl. All right, from the next one, sodium and nitrogen. If we look at the electronegativities, I'm not going to go back, but the electronegativity of sodium is 0.9, and the electronegativity of nitrogen is 3. I just pulled those straight from the chart. If I subtract them, we get a difference of 2.1, which is greater than 1.6, so we know it's an ionic bond. Okay, now for the Lewis dot structure, all right, nitrogen is in column 5A, so it's going to have 5 valence electrons. Okay, and then sodium, which is in A, is in column 1, so it's going to have 1 valence electron. Okay, so when I draw this, notice whenever I put them in, remember you do the first 4 sides first, then you start pairing them up. Okay, I'm not having these that are paired over here. Okay, so it's important to note that nitrogen has 3 unpaired electrons. Okay, and so because nitrogen has 3 unpaired electrons, whenever we go to do step 3, where we remove unpaired electrons, if I only have 1 sodium, nitrogen will still have 2 valence electrons that are unpaired, and it's not going to be happy. So basically what happens is 2 more sodium atoms have to come in and give their electron to nitrogen. Okay, so each individual sodium has only lost 1 electron. Okay, it's not losing 3. This one single sodium is not losing 3 electrons. It's only losing 1. There happens to be 3 sodium atoms. Okay, compared to nitrogen, nitrogen has gained 3 electrons. So it's going to have an oxidation number of -3. Okay, so the ion numbers, the sodium, if we just look at one single sodium, is going to be +1 because it lost 1 electron. Nitrogen has gained 3 electrons, so it's going to become -3. Okay, and so when we go to write the formula, there had to be 3 sodiums bonded with the nitrogen for them to become stable. Okay, so our formula is going to be Na3N. Okay, and so I want to talk real quick about the oxidation numbers. So if we look at sodium and nitrogen back here, okay, sodium again is oxidation is +1, which is what we found. Nitrogen is -3. Okay, so we can kind of look at atoms in this way and just look at oxidation and determine how many of each we're going to need. So if I was bonding oxygen and lithium, let's say lithium and oxygen, okay, lithium has an oxidation of +1, oxygen has a -2, okay, so in this case we would need 2 lithiums, right, so that it would be a +2 in total to match the oxygens of -2, okay? If I had like fluorine and beryllium, and I was putting those together, okay, I have +2 for beryllium, and I have -1 for fluorine, I would need 2 fluorines to accept the 2 electrons from beryllium, okay? So it would be 1 beryllium to 2 fluorines, okay? If I had, let's say, fluorine and boron, okay? Fluorine has -1, boron has +3, so I would need 3 fluorines in order to accept the 3 electrons that boron is going to give away. Okay, so that's just kind of an example of how you can use the valence or the oxidation number in order to determine what your chemical formula is going to be.